Chaos theory. For other uses, see chaos theory, disambiguation, and chaos, disambiguation. A plot of the Lorentz attractor for values R equals 28, sigma equals 10, B equals 8/3. An animation of a double rod pendulum at an intermediate energy showing chaotic behavior. Starting the pendulum from a slightly different initial condition would result in a vastly different trajectory. The double rod pendulum is one of the simplest dynamical systems with chaotic solutions. Chaos theory is an interdisciplinary theory and branch of mathematics focusing on the study of chaos, dynamical systems whose apparently random states of disorder and irregularities are actually governed by underlying patterns and deterministic laws that are highly sensitive to initial conditions. 1-2 Chaos theory states that within the apparent randomness of chaotic complex systems, there are underlying patterns, interconnectedness, constant feedback loops, repetition, self-similarity, fractals, and self-organization. 3. The butterfly effect, an underlying principle of chaos, describes how a small change in one state of a deterministic nonlinear system can result in large differences in a later state, meaning that there is sensitive dependence on initial conditions. 4. A metaphor for this behavior is that a butterfly flapping its wings in Brazil can cause a tornado in Texas. 5. Small differences in initial conditions, such as those due to errors in measurements or due to rounding errors in numerical computation, can yield widely diverging outcomes for such dynamical systems, rendering long-term prediction of their behavior impossible in general. 6. This can happen even though these systems are deterministic, meaning that their future behavior follows a unique evolution. 7. And is fully determined by their initial conditions, with no random elements involved. 8. In other words, the deterministic nature of these systems does not make them predictable. 9-10 This behavior is known as deterministic chaos, or simply chaos. The theory was summarized by Edward Lorenz as 11. Chaos, when the present determines the future, but the approximate present does not approximately determine the future. Chaotic behavior exists in many natural systems, including fluid flow, heartbeat irregularities, weather, and climate. 12-13-7 It also occurs spontaneously in some systems with artificial components, such as the stock market and road traffic. 14-3 This behavior can be studied through the analysis of a chaotic mathematical model, or through analytical techniques such as recurrence plots and Poincaré maps. Chaos theory has applications in a variety of disciplines, including meteorology, 7 anthropology, 15 sociology, environmental science, computer science, engineering, economics, ecology, pandemic crisis management, 16-17. The theory formed the basis for such fields of study as complex dynamical systems, edge of chaos theory, and self-assembly processes. Introduction. Chaos theory concerns deterministic systems whose behavior can, in principle, be predicted. Chaotic systems are predictable for a while and then appear to become random. The amount of time that the behavior of a chaotic system can be effectively predicted depends on three things: how much uncertainty can be tolerated in the forecast, how accurately its current state can be measured, and a time scale depending on the dynamics of the system, called the Lyapunov time. Some examples of Lyapunov times are chaotic electrical circuits, about 1 millisecond, weather systems, a few days, unproven, the inner solar system, 4 to 5 million years. 18 In chaotic systems, the uncertainty in a forecast increases exponentially with elapsed time. Hence, mathematically, doubling the forecast time more than squares the proportional uncertainty in the forecast. This means, in practice, a meaningful prediction cannot be made over an interval of more than 2 or 3 times the Lyapunov time. When meaningful predictions cannot be made, the system appears random. 19. Chaos theory is a method of qualitative and quantitative analysis to investigate the behavior of dynamic systems that cannot be explained and predicted by single data relationships, but must be explained and predicted by whole, continuous data relationships. Chaotic dynamics. In common usage, chaos means a state of disorder. 2021, however, in chaos theory, the term is defined more precisely. Although no universally accepted mathematical definition of chaos exists, a commonly used definition, originally formulated by Robert L. Devaney, says that to classify a dynamical system as chaotic, it must have these properties. 22. It must be sensitive to initial conditions. It must be topologically transitive. It must have dense periodic orbits. In some cases, the last two properties above have been shown to actually imply sensitivity to initial conditions. 23-24 In the discrete time case, this is true for all continuous disambiguation needed maps on metric spaces. 25 In these cases, while it is often the most practically significant property, sensitivity to initial conditions need not be stated in the definition. If attention is restricted to intervals, the second property implies the other two. 26 An alternative and a generally weaker definition of chaos uses only the first two properties in the above list. 27. Chaos as a spontaneous breakdown of topological supersymmetry. Main article, Supersymmetric Theory of Stochastic Dynamics. In continuous time dynamical systems, chaos is the phenomenon of the spontaneous breakdown of topological supersymmetry, which is an intrinsic property of evolution operators of all stochastic and deterministic, partial, differential equations. 28-29 This picture of dynamical chaos works not only for deterministic models, but also for models with external noise, which is an important generalization from the physical point of view, since in reality, all dynamical systems experience influence from their stochastic environments. Within this picture, the long-range dynamical behavior associated with chaotic dynamics, example the butterfly effect, is a consequence of Goldstone's theorem in the application to the spontaneous topological supersymmetry breaking. Sensitivity to initial conditions. Main article, Butterfly effect. Lorentz equations used to generate plots for the y variable. The initial conditions for x and z were kept the same, but those for y were changed between 1.001, 1.0001, and 1.00001. The values for \display style \rho \display style \sigma and \display style \beta were 45.92, 16, and 4 respectively. As can be seen from the graph, even the slightest difference in initial values causes significant changes after about 12 seconds of evolution in the three cases. This is an example of sensitive dependence on initial conditions. Sensitivity to initial conditions means that each point in a chaotic system is arbitrarily closely approximated by other points that have significantly different future paths or trajectories. Thus, an arbitrarily small change or perturbation of the current trajectory may lead to significantly different future behavior. 3. Sensitivity to initial conditions is popularly known as the butterfly effect, so called because of the title of a paper given by Edward Lorentz in 1972 to the American Association for the Advancement of Science in Washington, D.C. Entitled Predictability, Does the Flap of a Butterfly's Wings in Brazil Set Off a Tornado in Texas? 30 The flapping wing represents a small change in the initial condition of the system, which causes a chain of events that prevents the predictability of large-scale phenomena. Had the butterfly not flapped its wings, the trajectory of the overall system could have been vastly different. A consequence of sensitivity to initial conditions is that if we start with a limited amount of information about the system, as is usually the case in practice, then beyond a certain time, the system would no longer be predictable. This is most prevalent in the case of weather, which is generally predictable only about a week ahead. 31 This does not mean that one cannot assert anything about events far in the future, only that some restrictions on the system are present. For example, we do know with weather that the temperature will not naturally reach 100 degrees Celsius or fall to 130 degrees C on Earth during the current geologic era, but but that does not mean that we can predict exactly which day will have the hottest temperature of the year. In more mathematical terms, the Lyapunov exponent measures the sensitivity to initial conditions, in the form of rate of exponential divergence from the perturbed initial conditions. 32 More specifically, given two starting trajectories in the phase space that are infinitesimally close, with initial separation \displaystyle \delta\math z_0 \delta\math z_0, the two trajectories end up diverging at a rate given by \displaystyle \delta\math z t \approximate e caret \lambda t \delta \math z_0 comma \displaystyle \delta \math z t \approximate e caret \lambda t \delta \math z_0 comma, where \displaystyle tt is the time and \displaystyle \lambda is the Lyapunov exponent. The rate of separation depends on the orientation of the initial separation vector, so a whole spectrum of Lyapunov exponents can exist. The number of Lyapunov exponents is equal to the number of dimensions of the phase space, though it is common to just refer to the largest one. For example, the maximal Lyapunov exponent, MLE, is most often used, because it determines the overall predictability of the system. A positive MLE is usually taken as an indication that the system is chaotic. 7. In addition to the above property, other properties related to sensitivity of initial conditions also exist. These include, for example, measure theoretical mixing, as discussed in ergodic theory, and properties of a K-system. 10. Non-periodicity. A chaotic system may have sequences of values for the evolving variable that exactly repeat themselves, giving periodic behavior starting from any point in that sequence. However, such periodic sequences are repelling rather than attracting, meaning that if the evolving variable is outside the sequence, however close, it will not enter the sequence and in fact, will diverge from it. Thus for almost all initial conditions, the variable evolves chaotically with non-periodic behavior. Topological mixing. Topological mixing, or the weaker condition of topological transitivity, means that the system evolves over time so that any given region or open set of its phase space eventually overlaps with any other given region. This mathematical concept of mixing corresponds to the standard intuition, and the mixing of colored dyes or fluids is an example of a chaotic system. Topological mixing is often omitted from popular accounts of chaos, which equate chaos with only sensitivity to initial conditions. However, sensitive dependence on initial conditions alone does not give chaos. For example, consider the simple dynamical system produced by repeatedly doubling an initial value. This system has sensitive dependence on initial conditions everywhere, since any pair of nearby points eventually becomes widely separated. However, this example has no topological mixing, and therefore has no chaos. Indeed, it has extremely simple behavior. All points except 0 tend to positive or negative infinity. Topological transitivity. A map \displaystyle fx \2x \displaystyle fx \2x is said to be topologically transitive if for any pair of non-empty open sets \displaystyle uv \subset x \displaystyle uv \subset x. There exists \displaystyle k0 such that \displaystyle f caret k u \cap v \nuc empty set \displaystyle f caret k u \cap v \nuc empty set. Topological transitivity is a weaker version of topological mixing. Intuitively, if a map is topologically transitive, then given a point x and a region v, there exists a point y near x whose orbit passes through v. This implies that it is impossible to decompose the system into two open sets. 33. An important related theorem is the Birkhoff transitivity theorem. It is easy to see that the existence of a dense orbit implies in topological transitivity. The Birkhoff transitivity theorem states that if X is a second countable, complete metric space, then topological transitivity implies the existence of a dense set of points in X that have dense orbits. 34. Density of periodic orbits. For a chaotic system to have dense periodic orbits means that every point in the space is approached arbitrarily closely by periodic orbits. 33. The one-dimensional logistic map defined by X rightward arrow for X, 1, X, is one of the simplest systems with density of periodic orbits. For example, \display style \tfrac5 \sqrt58 \tfrac5 \sqrt58 rightward arrow \display style \tfrac5 plus \sqrt58 \tfrac5 plus \sqrt58 rightward arrow \display style \tfrac5 \sqrt58 \tfrac5 \sqrt58, or approximately 0.34549115 rightward arrow 0.9045085 rightward arrow 0.34549115, is an unstable orbit of period 2, and similar orbits exist for periods 4, 8, 16, etc. Indeed, for all the periods specified by Sharkovsky's theorem. 35. Sharkovsky's theorem is the basis of the Lee and York 36, 1975, proved that any continuous one-dimensional system that exhibits a regular cycle of period 3 will also display regular cycles of every other length, as well as completely chaotic orbits. Strange attractors. The Lorentz attractor displays chaotic behavior. These two plots demonstrate sensitive dependence on initial conditions within the region of phase space occupied by the attractor. Some dynamical systems, like the one-dimensional logistic map defined by X rightward arrow for X, 1, X, are chaotic everywhere, but in many cases chaotic behavior is found only in a subset of phase space. The cases of most interest arise when the chaotic behavior takes place on an attractor, since then a large set of initial conditions leads to orbits that converge to this chaotic region. 37. An easy way to visualize a chaotic attractor is to start with a point in the basin of attraction of the attractor, and then simply plot its subsequent orbit. Because of the topological transitivity condition, this is likely to produce a picture of the entire final attractor, and indeed both orbits shown in the figure on the right give a picture of the general shape of the Lorentz attractor. This attractor results from a simple three-dimensional model of the Lorentz weather system. The Lorentz attractor is perhaps one of the best-known chaotic system diagrams, probably because it is not only one of the first, but it is also one of the most complex, and as such gives rise to a very interesting pattern that, with a little imagination, looks like the wings of a butterfly. Unlike fixed-point attractors and limit cycles, the attractors that arise from chaotic systems, known as strange attractors, have great detail and complexity. Strange attractors occur in both continuous dynamical systems, such as the Lorentz system, and in some discrete systems, such as the Henin map. Other discrete dynamical systems have a repelling structure called a Julia set, which forms at the boundary between basins of attraction of fixed points. Julia sets can be thought of as strange repellers. Both strange attractors and Julia sets typically have a fractal structure, and the fractal dimension can be calculated for them. Minimum complexity of a chaotic system. Bifurcation diagram of the logistic map X rightward arrow Rx, 1, X. Each vertical slice shows the attractor for a specific value of R. The diagram displays period doubling as R increases, eventually producing chaos. Discrete chaotic systems, such as the logistic map, can exhibit strange attractors whatever their dimensionality. Universality of one-dimensional maps with parabolic maxima and Feigenbaum constants \display style \delta equals 4.669201. \display style \delta equals 4.669201. backslash display style backslash alpha equals 2.502907. Backslash display style backslash alpha equals 2.502907. 3839 is well visible with map proposed as a toy model for discrete laser dynamics. Backslash display style x backslash right arrow gx 1 dash backslash mathrm 10 x backslash display style x backslash right arrow gx 1 dash backslash mathrm 10 x, where backslash display style xx stands for electric field amplitude. Backslash display style GG40 is laser gain as bifurcation parameter. The gradual increase of backslash display style GG at interval backslash display style 0 backslash int t, 0 backslash int t, changes dynamics from regular to chaotic 141 with qualitatively the same bifurcation diagram as those for logistic map. In contrast, for continuous dynamical systems, the Poincaré-Bendixson theorem shows that a strange attractor can only arise in 3 or more dimensions. Finite-dimensional linear systems are never chaotic. For a dynamical system to display chaotic behavior, it must be either nonlinear or infinite-dimensional. The Poincaré-Bendixson theorem states that a two-dimensional differential equation has very regular behavior. The Lorentz attractor discussed below is generated by a system of 3 differential equations such as backslash display style backslash begin aligned backslash frac backslash mathrm dx backslash mathrm dt and equals backslash sigma y dash backslash sigma x backslash frac backslash mathrm dy backslash mathrm dt and equals backslash rho xxzy backslash frac backslash mathrm dz backslash mathrm dt and equals xy dash backslash beta z backslash end aligned backslash begin aligned backslash frac backslash mathrm dx backslash mathrm dt and equals backslash sigma y dash backslash sigma x backslash left brace backslash fra c backslash mathrm dy backslash mathrm dt and equals backslash rho xxzy backslash frac backslash mathrm dz backslash mathrm dt and equals xy dash backslash beta z backslash end aligned, where backslash display style xx backslash display style yy and backslash display style zz make up the system state, backslash display style tt is time, and backslash display style backslash sigma backslash display style backslash rho backslash display style backslash beta are the system parameters. 5 of the terms on the right hand side are linear, while 2 are quadratic, a total of 7 terms. Another well-known chaotic attractor is generated by the Rossler equations, which have only one nonlinear term out of 7. Sprott 42 found a 3-dimensional system with just 5 terms, that had only one nonlinear term, which exhibits chaos for certain parameter values. Zhang and Heidel 43-44 showed that, at least for dissipative and conservative quadratic systems, 3-dimensional quadratic systems with only 3 or 4 terms on the right-hand side cannot exhibit chaotic behavior. The reason is, simply put, that solutions to such systems are asymptotic to a 2-dimensional surface and therefore solutions are well behaved. While the Poincaré-Bendixson theorem shows that a continuous dynamical system on the Euclidean plane cannot be chaotic, 2-dimensional continuous systems with non-Euclidean geometry can exhibit chaotic behavior. 45 self-published source. Perhaps surprisingly, chaos may occur also in linear systems, provided they are infinite dimensional. 46 A theory of linear chaos is being developed in a branch of mathematical analysis known as functional analysis. Infinite dimensional maps. The straightforward generalization of coupled discrete maps 47 is based upon convolution integral which mediates interaction between spatially distributed maps, backslash display style backslash psi underscore n plus 1, backslash vec rt, equals backslash int k, backslash vec r dash backslash vec r caret comma t, f backslash psi underscore n, backslash vec r caret comma t, d backslash vec r caret. Backslash display style backslash psi underscore n plus 1, backslash vec rt, equals backslash int k, backslash vec r dash backslash vec r caret comma t, f backslash psi underscore n, backslash vec r caret comma t, d backslash vec r caret comma, where kernel backslash display style k, backslash vec r dash backslash vec r caret comma t, backslash display style k, backslash vec r dash backslash vec r caret comma t, is propagator derived as green function of a relevant physical system 48 backslash display style f backslash psi underscore n, backslash vec rt, backslash display style f backslash psi underscore n, backslash vec r t, might be logistic map alike backslash display style backslash psi backslash right arrow g backslash psi 1 dash backslash 10, backslash psi, backslash display style backslash psi backslash right arrow g backslash psi 1 dash backslash 10, backslash psi, or complex map. For examples of complex maps, the Julia set backslash display style f backslash psi equals backslash psi caret 2 backslash display style f backslash psi equals backslash psi caret 2 or Ikeda map backslash display style backslash psi underscore n plus 1 equals a plus b backslash psi underscore n e caret I, backslash psi underscore n caret 2 plus c, backslash display style backslash psi underscore n plus 1 equals a plus b backslash psi underscore n e caret I, backslash psi underscore n caret 2 plus c, may serve. When wave propagation problems at distance backslash display style L equals CT backslash display style L equals CT with wavelength backslash display style backslash lambda equals 2 backslash pi slash k backslash lambda equals 2 backslash pi slash k are considered, the kernel backslash display style kk may have a form of green function for Schrödinger equation. 4950. Backslash display style k, backslash vec r dash backslash vec r caret comma l, equals backslash fracc backslash exp l2 backslash pi l backslash exp backslash fracc backslash vec r dash backslash vec r caret comma caret 2 2l backslash display style k, backslash vec r dash backslash vec r caret comma l, equals backslash fracc backslash exp l2 backslash pi l backslash exp backslash fracc backslash vec r dash backslash vec r caret comma caret 2 2l. Jerk systems. In physics, jerk is the third derivative of position with respect to time. As such, differential equations of the form backslash display style j backslash left backslash overset x comma backslash dot x comma backslash dot x x backslash right equals 0 j backslash left backslash overset x comma backslash dot x comma backslash dot x x backslash right equals 0 are sometimes called jerk equations. It has been shown that a jerk equation, which is equivalent to a system of three first-order, ordinary, nonlinear differential equations, is in a certain sense the minimal setting for solutions showing chaotic behavior. This motivates mathematical interest in jerk systems. Systems involving a fourth or higher derivative are called accordingly hyperjerk systems. 51. A jerk system's behavior is described by a jerk equation, and for certain jerk equations, simple electronic circuits can model solutions. These circuits are known as jerk circuits. One of the most interesting properties of jerk circuits is the possibility of chaotic behavior. In fact, certain well-known chaotic systems, such as the Lorentz attractor and the Rosseler map, are conventionally described as a system of three first-order differential equations that can combine into a single, although rather complicated, jerk equation. Another example of a jerk equation with nonlinearity in the magnitude of backslash display style xx is backslash display style backslash frac backslash mathrm d caret 3x backslash mathrm dt caret 3 plus a backslash frac backslash mathrm d caret 2x backslash mathrm dt caret 2 plus backslash frac backslash mathrm dx backslash mathrm dt dash x plus 1 equals 0. Backslash frac backslash mathrm d caret 3x backslash mathrm dt caret 3 plus a backslash frac backslash mathrm d caret 2x backslash mathrm dt caret 2 plus backslash frac backslash mathrm dx backslash mathrm dt dash x plus 1 equals 0. Here, a is an adjustable parameter. This This equation has a chaotic solution for A equals 3/5 and can be implemented with the following jerk circuit. The required nonlinearity is brought about by the two diodes. Jerk circuit 01.png. In the above circuit, all resistors are of equal value, except \display style r_a equals r/a equals 5 r/3 r_a equals r/a equals 5 r/3, and all capacitors are of equal size. The dominant frequency is \display style 1/2 \pi rc 1/2 \pi rc. The output of op-amp 0 will correspond to the x variable, the output of 1 corresponds to the first derivative of x, and the output of 2 corresponds to the second derivative. Similar circuits only require one diode. 52 or no diodes at all. 53. See also the well-known Chua circuit, one basis for chaotic true random number generators. 54. The ease of construction of the circuit has made it a ubiquitous real-world example of a chaotic system. Spontaneous order. Under the right conditions, chaos spontaneously evolves into a lockstep pattern. In the Kuramoto model, 4 conditions suffice to produce synchronization in a chaotic system. Examples include the coupled oscillation of Christian-Huygens pendulums, fireflies, neurons, the London Millennium Bridge resonance, and large arrays of Josephson junctions. 55. History. An early proponent of chaos theory was Henri Poincaré. In the 1880s, while studying the three-body problem, he found that there can be orbits that are non-periodic, and yet not forever increasing nor approaching a fixed point. 56, 57, 58. In 1898, Jacques Hadamard published an influential study of the chaotic motion of a free particle gliding frictionlessly on a surface of constant negative curvature, called Hadamard's billiards. 59. Hadamard was able to show that all trajectories are unstable, in that all particle trajectories diverge exponentially from one another, with a positive Lyapunov exponent. Chaos theory began in the field of ergodic theory. Later studies, also on the topic of nonlinear differential equations, were carried out by George David Birkhoff 60, Andrei Nikolaevich Kolmogorov 61, 62, 63, Mary Lucy Cartwright and John Edenser Littlewood 64, and Stephen Smale 65. Except for Smale, these studies were all directly inspired by physics, the three-body problem in the case of Birkhoff, turbulence and astronomical problems in the case of Kolmogorov, and radio engineering in the case of Cartwright and Littlewood. Citation needed. Although chaotic planetary motion had not been observed, experimentalists had encountered turbulence in fluid motion and non-periodic oscillation in radio circuits without the benefit of a theory to explain what they were seeing. Despite initial insights in the first half of the 20th century, chaos theory became formalized as such only after mid-century, when it first became evident to some scientists that linear theory, the prevailing system theory at that time, simply could not explain the observed behavior of certain experiments like that of the logistic map. What had been attributed to measure imprecision and simple noise was considered by chaos theorists as a full component of the studied systems. The main catalyst for the development of chaos theory was the electronic computer. Much of the mathematics of chaos theory involves the repeated iteration of simple mathematical formulas, which would be impractical to do by hand. Electronic computers made these repeated calculations practical, while figures and images made it possible to visualize these systems. As a graduate student in Chihiro Hayashi's laboratory at Kyoto University, Yoshi Sugueta was experimenting with analog computers and noticed, on November 27, 1961, what he called randomly transitional phenomena. Yet his advisor did not agree with his conclusions at the time, and did not allow him to report his findings until 1970. 66-67. Edward Lorenz was an early pioneer of the theory. His interest in chaos came about accidentally through his work on weather prediction in 1961. Lorenz was using a simple digital computer, a Royal McBee LGP30, to run his weather simulation. He wanted to see a sequence of data again, and to save time he started the simulation in the middle of its course. He did this by entering a printout of the data that corresponded to conditions in the middle of the original simulation. To his surprise, the weather the machine began to predict was completely different from the previous calculation. Lorentz tracked this down to the computer printout. The computer worked with 6-digit precision, but the printout rounded variables off to a 3-digit number, so a value like 0.506127 printed as 0.506. This difference is tiny, and the consensus at the time would have been that it should have no practical effect. However, Lorentz discovered that small changes in initial conditions produced large changes in long-term outcome. 68 Lorentz's discovery, which gave its name to Lorentz attractors, showed that even detailed atmospheric modeling cannot, in general, make precise long-term weather predictions. In 1963, Benoit Mandelbrot found recurring patterns at every scale in data on cotton prices. 69 beforehand he had studied information theory and concluded noise was patterned like a Cantor set. On any scale the proportion of noise-containing periods to error-free periods was a constant, thus errors were inevitable and must be planned for by incorporating redundancy. 70 Mandelbrot described both the Noah effect, in which sudden discontinuous changes can occur, and the Joseph effect, in which persistence of a value can occur for a while, yet suddenly change afterwards. 71-72 This challenged the idea that changes in price were normally distributed. In 1967, he published How Long is the Coast of Britain? Statistical Self-Similarity and Fractional Dimension, showing that a coastline's length varies with the scale of the measuring instrument, resembles itself at all scales, and is infinite in length for an infinitesimally small measuring device. 73 Arguing that a ball of twine appears as a point when viewed from far away, 0-dimensional, a ball when viewed from fairly near, 3-dimensional, or a curved strand, 1-dimensional, he argued that the dimensions of an object are relative to the observer and may be fractional. An object whose irregularity is constant over different scales, self-similarity, is a fractal. Examples include the Menger sponge, the Sierpinski gasket, and the Cook curve or snowflake, which is infinitely long yet encloses a finite space and has a fractal dimension of circa 1.2619. In 1982, Mandelbrot published The Fractal Geometry of Nature, which became a classic of chaos theory. 74 Biological systems such as the branching of the circulatory and bronchial systems proved to fit a fractal model. 75. In December 1977, the New York Academy of Sciences organized the first symposium on chaos, attended by David Ruel, Robert May, James A. York, coiner of the term chaos as used in mathematics, Robert Shaw, and the meteorologist Edward Lorenz. The following year Pierre Calliot and Charles Tresser published Iterations d'endomorphisms et group de renormalization, and Mitchell Feigenbaum's article Quantitative Universality for a Class of Nonlinear Transformations finally appeared in a journal, after 3 years of referee rejections. 3976 Thus Feigenbaum, 1975, and Calliot and Tresser, 1978, discovered the universality in chaos, permitting the application of chaos theory to many different phenomena. In 1979, Albert J. Lipchaber, during a symposium organized in Aspen by Pierre Hohenberg, presented his experimental observation of the bifurcation cascade that leads to chaos and turbulence in Rayleigh-Benard convection systems. He was awarded the Wolf Prize in Physics in 1986 along with Mitchell J. Feigenbaum for their inspiring achievements. 77. In 1986, the New York Academy of Sciences co-organized with the National Institute of Mental Health and the Office of Naval Research the first important conference on chaos in biology and medicine. There, Bernardo Huberman presented a mathematical model of the eye tracking disorder among schizophrenics. 78 This led to a renewal of physiology in the 1980s through the application of chaos theory, for example, in the study of pathological cardiac cycles. In 1987, Per Bach, Xiaotang and Kurt Wiesenfeld published a paper in Physical Review Letters 79 describing for the first time self-organized criticality, SOC, considered one of the mechanisms by which complexity arises in nature. Alongside largely lab-based approaches such as the Bach, Tang, Wiesenfeld sand pile, many other investigations have focused on large-scale natural or social systems that are known, or suspected, to display scale-invariant behavior. Although these approaches were not always welcomed, at least initially, by specialists in the subjects examined, SOC has nevertheless become established as a strong candidate for explaining a number of natural phenomena, including earthquakes, which, long before SOC was discovered, were known as a source of scale-invariant behavior such as the Gutenberg, Richter law describing the statistical distribution of earthquake sizes, and the Ohmura law 80 describing the frequency of aftershocks, solar flares. Fluctuations in economic systems such as financial markets, references to SOC are common in econophysics, landscape formation, forest fires, landslides, epidemics, and biological evolution, where SOC has been invoked, for example, as the dynamical mechanism behind the theory of punctuated equilibria put forward by Niles Eldredge and Stephen Jay Gould. Given the implications of a scale-free distribution of event sizes, some researchers have suggested that another phenomenon that should be considered an example of SOC is the occurrence of wars. These investigations of SOC have included both attempts at modeling, either developing new models or adapting existing ones to the specifics of a given natural system, and extensive data analysis to determine the existence and/or characteristics of natural scaling laws. In the same year, James Gleick published Chaos, Making a New Science, which became a bestseller and introduced the general principles of chaos theory as well as its history to the broad public, though his history underemphasized important Soviet contributions. Citation needed 81. Initially the domain of a few, isolated individuals, chaos theory progressively emerged as a transdisciplinary and institutional discipline, mainly under the name of nonlinear systems analysis. Alluding to Thomas Kuhn's concept of a paradigm shift exposed in The Structure of Scientific Revolutions, 1962, many chaologists, as some described themselves, claimed that this new theory was an example of such a shift, a thesis upheld by Gleick. The availability of cheaper, more powerful computers broadens the applicability of chaos theory. Currently, chaos theory remains an active area of research 82 involving many different disciplines such as mathematics, topology, physics 83 social systems 84 population modeling, biology, meteorology, astrophysics, information theory, computational neuroscience, pandemic crisis management, 1617 etc. Applications. Although chaos theory was born from observing weather patterns, it has become applicable to a variety of other situations. Some areas benefiting from chaos theory today are geology, mathematics, biology, computer science, economics 86, 87, 88, engineering 89, 90, finance 91, 92, algorithmic trading 93, 94, 95, meteorology, philosophy, anthropology 15, physics 96, 97, 98, politics 99, 100, population dynamics 101, psychology 14, and robotics. A few categories are listed below with examples, but this is by no means a comprehensive list as new applications are appearing. Cryptography. Chaos theory has been used for many years in cryptography. In the past few decades, chaos and nonlinear dynamics have been used in the design of hundreds of cryptographic primitives. These algorithms include image encryption algorithms, hash functions, secure pseudo-random number generators, stream ciphers, watermarking and steganography. 102. The majority of these algorithms are based on unimodal chaotic maps, and a big portion of these algorithms use the control parameters and the initial condition of the chaotic maps as their keys. 103. From a wider perspective, without loss of generality, The similarities between the chaotic maps and the cryptographic systems is the main motivation for the design of chaos-based cryptographic algorithms. 102. One type of encryption, secret key or symmetric key, relies on diffusion and confusion, which is modeled well by chaos theory. 104. Another type of computing, DNA computing, when paired with chaos theory, offers a way to encrypt images and other information. 105. Many of the DNA chaos cryptographic algorithms are proven to be either not secure, or the technique applied is suggested to be not efficient. 106, 107, 108. Robotics. Robotics is another area that has recently benefited from chaos theory. Instead of robots acting in a trial and error type of refinement to interact with their environment, chaos theory has been used to build a predictive model. 109. Chaotic dynamics have been exhibited by passive walking bipped robots. 110. Biology. For over 100 years, biologists have been keeping track of populations of different species with population models. Most models are continuous, but recently scientists have been able to implement chaotic models in certain populations. 111. For example, a study on models of Canadian lynx showed there was chaotic behavior in the population growth. 112. Chaos can also be found in ecological systems, such as hydrology. While a chaotic model for hydrology has its shortcomings, there is still much to learn from looking at the data through the lens of chaos theory. 113. Another biological application is found in cardiotocography. Fetal surveillance is a delicate balance of obtaining accurate information while being as non-invasive as possible. Better models of warning signs of fetal hypoxia can be obtained through chaotic modeling. 114. Economics. It is possible that economic models can also be improved through an application of chaos theory, but predicting the health of an economic system and what factors influence it most is an extremely complex task. 115. Economic and financial systems are fundamentally different from those in the classical natural sciences, since the former are inherently stochastic in nature, as they result from the interactions of people. And thus pure deterministic models are unlikely to provide accurate representations of the data. The empirical literature that tests for chaos in economics and finance presents very mixed results, in part due to confusion between specific tests for chaos and more general tests for nonlinear relationships. 116. Chaos could be found in economics by the means of recurrence quantification analysis. In fact, Orlando et al. 117. By the means of the so-called recurrence quantification correlation index were able to detect hidden changes in time series. Then, the same technique was employed to detect transitions from laminar, i.e. regular, to turbulent, i.e. chaotic, phases, as well as differences between macroeconomic variables and highlight hidden features of economic dynamics. 118. Finally, chaos could help in modeling how economy operate as well as in embedding shocks due to external events such as COVID-19. 119. For an updated account on the tools and the results obtained by empirically calibrating and testing deterministic chaotic models, e.g. Calder-Kalecki 120, Goodwin 121, Harrod 122, see Orlando et al. 123. Other areas. In chemistry, predicting gas solubility is essential to manufacturing polymers, but models using particle swarm optimization, PSO, tend to converge to the wrong points. An improved version of PSO has been created by introducing chaos, which keeps the simulations from getting stuck. 124. In celestial mechanics, especially when observing asteroids, applying chaos theory leads to better predictions about when these objects will approach Earth and other planets. 125. 4 of the 5 moons of Pluto rotate chaotically. In quantum physics and electrical engineering, the study of large arrays of Josephson junctions benefited greatly from chaos theory. 126. Closer to home, Coal mines have always been dangerous places where frequent natural gas leaks cause many deaths. Until recently, there was no reliable way to predict when they would occur. But these gas leaks have chaotic tendencies that, when properly modeled, can be predicted fairly accurately. 127. Chaos theory can be applied outside of the natural sciences, but historically nearly all such studies have suffered from lack of reproducibility, poor external validity, and/or inattention to cross-validation, resulting in poor predictive accuracy, if out-of-sample prediction has even been attempted. Glass 128 and Mandel and Cells 129 have found that no EEG study has as yet indicated the presence of strange attractors or other signs of chaotic behavior. Researchers have continued to apply chaos theory to psychology. For example, in modeling group behavior in which heterogeneous members may behave as if sharing to different degrees what in Wilfred Bian's theory is a basic assumption. Researchers have found that the group dynamic is the result of the individual dynamics of the members. Each individual reproduces the group dynamics in a different scale, and the chaotic behavior of the group is reflected in each member. 130. Reddington and Reed Board, 1992, attempted to demonstrate that the human heart could display chaotic traits. They monitored the changes in between heartbeat intervals for a single psychotherapy patient as she moved through periods of varying emotional intensity during a therapy session. Results were admittedly inconclusive. Not only were there ambiguities in the various plots the authors produced to purportedly show evidence of chaotic dynamics, spectral analysis, phase trajectory, and autocorrelation plots, but also when they attempted to compute a Lyapunov exponent as more definitive confirmation of chaotic behavior, the authors found they could not reliably do so. 131. In their 1995 paper, Metcalf and Allen 132 maintained that they uncovered in animal behavior a pattern of period doubling leading to chaos. The authors examined a well-known response called schedule-induced polydipsia, by which an animal deprived of food for certain lengths of time will drink unusual amounts of water when the food is at last presented. The control parameter, R, operating here was the length of the interval between feedings, once resumed. The authors were careful to test a large number of animals and to include many replications, and they designed their experiment so as to rule out the likelihood that changes in response patterns were caused by different starting places for R. Time series and first delay plots provide the best support for the claims made, showing a fairly clear march from periodicity to irregularity as the feeding times were increased. The various phase trajectory plots and spectral analyses, on the other hand, do not match up well enough with the other graphs or with the overall theory to lead inexorably to a chaotic diagnosis. For example, the phase trajectories do not show a definite progression towards greater and greater complexity, and away from periodicity, the process seems quite muddled. Also, where Metcalf and Allen saw periods of 2 and 6 in their spectral plots, there is room for alternative interpretations. All of this ambiguity necessitates some serpentine, post hoc explanation to show that results fit a chaotic model. By adapting a model of career counseling to include a chaotic interpretation of the relationship between employees and the job market, Amundsen and Bright found that better suggestions can be made to people struggling with career decisions. 133 Modern organizations are increasingly seen as open complex adaptive systems with fundamental natural nonlinear structures, subject to internal and external forces that may contribute chaos. For instance, team building and group development is increasingly being researched as an inherently unpredictable system, as the uncertainty of different individuals meeting for the first time makes the trajectory of the team unknowable. 134. Some say the chaos metaphor used in verbal theories grounded on mathematical models and psychological aspects of human behavior provides helpful insights to describing the complexity of small work groups that go beyond the metaphor itself. 135. The red cars and blue cars take turns to move, the red ones only move upwards, and the blue ones move rightwards. Every time, All the cars of the same color try to move one step if there is no car in front of it. Here, the model has self-organized in a somewhat geometric pattern where there are some traffic jams and some areas where cars can move at top speed. Traffic forecasting may benefit from applications of chaos theory. Better predictions of when traffic will occur would allow measures to be taken to disperse it before it would have occurred. Combining chaos theory principles with a few other methods has led to a more accurate short-term prediction model. See the plot of the BML traffic model at right. 136. Chaos theory has been applied to environmental water cycle data, aka hydrological data, such as rainfall and stream flow. 137. These studies have yielded controversial results, because the methods for detecting a chaotic signature are often relatively subjective. Early studies tended to succeed in finding chaos, whereas subsequent studies and meta-analyses called those studies into question and provided explanations for why these datasets are not likely to have low-dimension chaotic dynamics.